Hello and welcome to Math 253, Calculus 3 here at Cañada College. My name is Lapuz. In this video we will go over checkpoint 6.65 from our OpenStax textbook. And in this problem they're asking us to verify the divergence theorem for the vector field f is equal to x plus y plus z in the first component, y in the second component, and 2x minus y in the third component. Our surface is going to be a cylinder. X squared plus y squared is equal to 1. For z going from 0 to 3, and that would have to include the top and the bottom, otherwise it's not a closed curve. So this is what we have. We have a flux integral over a surface that is closed of the vector field, and according to the divergence theorem this is supposed to be equal to the triple integral of E of the div of your vector field dv, where E is going to be the solid and S is going to be the boundary of E. So S has to be closed and boundary of the solid E. Okay, so they want us to verify, which is probably means to do both sides and make sure that they are going to be equal. Now let's take a look at this surface again. This is a cylinder. X squared plus y squared is equal to 1, and that is going to go from 0 to 3. So this is your surface, and it has the top and the bottom closed off, and so the E is the solid itself, where S is equal to this. Now if you were to do this directly, which is what they're asking us to do, is they're asking us to verify, we have to actually split this up to 3 different integrals. So let's say S1 is the cylinder itself, the sides, S2 is the bottom, and S3 is the top. So this will actually, this flux of a closed surface will actually be equal to three surface integrals. So surface integral over S, surface integral over S1, S2, and then a surface integral over S3. Now these are not closed surfaces anymore, so we don't put this symbol there. These are just regular surfaces. So we will need to parameterize each one of these surfaces. Let's try S1 first. Now this parameterization here will not be a graph parameterization. You will have to actually be creative and use cylindrical coordinates. R is going to be a fixed radius. R is going to be equal to 1 in polar coordinates or cylindrical coordinates. So your variables are going to be theta and z. You can call them u and v, which is what we normally do, but let's actually stick with the cylindrical coordinate variables, and that's theta and z. And again, r is constant at 1, so we don't include that as part of the parameterization. So our x is going to be r, that's 1 times cosine of theta. Our y is going to be r sine theta, and our z is going to be z. Now we want to identify the domain as soon as we can. Our domain here now is going to say that theta is going to go from 0 to 2 pi, and then your z will go from 0 to 3, as they stated. All right. And now we have to find the cross product, RU or R theta. So we need to take the derivative of this thing with respect to theta. And I'm sorry, the R here is for radial distance in polar coordinates, and this R is the parameterization vector function that we use. So it's different from the r radial distance in polar or cylindrical coordinates. Anyways, r theta, the derivative with respect to theta, negative sine theta, positive cosine theta, and this is going to be 0 because there's no thetas involved there. Rz is going to be equal to no z's in the first two components, and then the last one is 1. And then when we cross them, r theta cross rz to get our normal vector, we will get, see, and the x component is going to be cosine theta, comma, and the y component is negative, and then that's going to give us a negative sign, so that's going to make it positive sine theta. And then the last component will be 0. And that does make sense because our vector, our theta, our sine and theta, sine and cosine of theta is just going to be like in going around in circular fashion, and there's no movement in the z. These normal vectors are perfectly horizontal. Okay, so that is our r. Now we need to figure out what our function is, our vector field, what that is when we evaluate it with r, the parameterization. And so wherever we see an x, we will put a cosine theta. So this is cosine theta, plus wherever we see y, we put sine theta, and wherever we see a z, we put z. And then our y is going to be, again, sine theta. And then we have 2 cosine theta minus sine theta. So that is our f vector. We will need to dot it with this. So f of r of theta z dotted with r theta cross rz. So the first component will tack on a cosine. So that's cosine theta, and then let's just rewrite everything over and figure out how to simplify afterwards. So we got cosine theta times cosine theta plus sine theta plus z. Next we have sine theta times sine theta. And we're adding this because we're doing a dot product, so that's sine theta quantity squared. And then finally we get a 0. All right, let's keep working on this to simplify it before we put it in an integral. We got the cosine squared theta plus cosine theta sine theta plus z cosine theta. And then we have the sine squared theta. So this, the first and last terms here will amount to 1. So let's just put that in the beginning. 1 plus cosine theta sine theta plus z cosine theta. Okay. All right. So that is the thing that we are going to integrate. And if we do that, let's get it into our integral. So our double integral, we are looking at the integral of S1. That's this integral right here of f dotted with ds, and we got everything simplified here. So this is a double integral over d, and this is our d, remember, our domain, and this will equal to 1 plus cosine theta sine theta plus z cosine theta d theta, or d a, let's call it dA. A is going to be dz d theta or d theta dz, whatever order we want. And it looks like they're both constants, or both limits are constants all the way around, so it's not going to matter which one we do first. So let's integrate 1 plus cosine theta sine theta plus z cosine theta, and then let's say dz first, going from 0 to 3, and then d theta going from 0 to 2 pi. Okay, now we just have to do some integrals. It turns out that we can split this up to 3 separate integrals, and I do want to point out a couple of things. The double integral of 1 dz d theta, where z goes from 0 to 3 and theta goes from 0 to 2 pi, it's going to give us a z, and then z goes from 0 to 3, so that's going to be a 3, and then it's going to give us a theta, where theta goes from 0 to 2 pi, so that's just 2 pi. So this is going to be 6 pi. Alright, now for the next integral, we got the double integral of cosine theta sine theta dz d theta. Z goes from 0 to 3, and theta goes from 0 to 2 pi. Now let's get rid of the z, so that's just going to be the integral with respect to z is going to be z, and z from 0 to 3 is going to be 3. So this is separate. This is going to be 3 from our z integral, and integral from 0 to 2 pi of cosine theta sine theta. And if you do a u substitution where u is equal to sine, you're going to get sine squared over 2, and then you're going to put 0 and 2 pi in there, and that's really just going to give us 0. You should double check this. There's a couple of, so we could do this integral. I did this integral in my head. You can also use Wolfram alpha, or you can reason it out. You can graph this and see that this has one period going from 0 to 2 pi. So if this thing has one period where half the area is above the x-axis, half the area is below, then you're going to go from 0 to 2 pi. The areas are all going to cancel each other out. And the same is going to go for this last one. So a double integral is 0 to 3, 0 to 2 pi of z cosine theta dz d theta. Again, the cosine function from 0 to 2 pi, because that's the period. You got the area above and the area below the x-axis will cancel each other out. So this will give you 0 again. All right, so in short, what we got was this thing became 0, this thing became 0, and then this thing was 6 pi. So in general, as first integral, let's write it down over here. The double integral of S1 of f dot ds is going to be 6 pi. Okay, one down. Let's find the other surface. There's 2 more surfaces actually. Let's do S2, and S2 is the, let's do the bottom part of the cylinder first. Was that S2? I think that's, yeah, that's what we defined as S2. So S2 can be parameterized as a graph parameterization where you have x and y, and then that's going to be x, y, and then this is just the plane z is equal to 0, so that's just 0. Now your normal vector, if you do rx cross ry, it's going to be 0, 0, 1. So that is going up. That's your normal vector. But if you look at the original cylinder, to have the proper orientation, we want the orientation of this to be going outward. So in this closed boundary solid, closed boundary of the solid E, we want the orientation of that surface to be going out. So we have an opposite parameterization. I call it an orientation reversing parameterization, or you can just make a note for yourself that you want to throw a negative sign. You can throw a negative sign now, or you can throw a negative sign when you do the surface, the flux integral. All right, so let's do the flux integral, or we have to put this into the function first. Let's see, f of r of xy in this case. So we had r theta before because those are the variables in our parameterization. This time we have x and y. And then we have, this is our vector field. So x plus y plus z, x plus y plus z is equal to 0 here. So that's going to be 0. And then the second component is y, and the third component is 2x minus y. Okay. And then now if you take the dot product of f dotted with a normal, rx cross ry, you'll see that you have 0 for the x, 0 for the y, and all you have left is 2x minus y. Let me verify that just to make sure. Yeah, 2x minus y. Okay. We did not establish our domain of integration, and so let's just do it here now. The domain is going to be, I don't like describing this in Cartesian coordinates, so I usually just draw it because I'm going to go into polar coordinates. Our domain is just on the xy plane. It's going to be a disk of radius 1. So that's going to go polar coordinates, where r is going to go from 0 to 1, theta goes from 0 to 2 pi. All right, so our second integral, S2 of f ds, the flux integral, that's going to be the double integral over d. Let's call this d2 since this is our second one. And then this is what we ended up with, 2x minus y dA. Now, we're going to go to polar coordinates at this point. So 2 times r cosine theta minus r sine theta. So we have the x and the y got changed into polar coordinates. And remember that you have to include the r, dr, d theta. R goes from our domain. R goes from 0 to 1. And theta goes all the way around from 0 to 2 pi. Okay. Now, I think we can see the same sort of situation here. This time it's actually nicer because I can take the r's out and separate this because these are just factors. So I'm going to go integrate from 0 to 1 of r squared dr. So that's this r over here, and these two r's factor out together to make another r. So that's r squared. And then I would have left over from 0 to 2 pi the integral of 2 cosine theta minus sine theta d theta. So this is going to be whatever that is. And again, when we integrate the integral from 0 to 2 pi cosine theta, because the cosine, whether it's, let's call the amplitude 2, the area on top and the area on the bottom is going to be the same. So this is going to give you 0. And the sine, the same thing. From 0 to 2 pi, those areas are going to be the same, one on top and one on the bottom, so that's going to be 0 as well. So this whole thing is going to give a contribution of 0. All right, one more surface to go, and that surface will come from the top of the cylinder, which is essentially the same as this one. So S3 is the top of the cylinder. That's going to get parameterized with r of xy, graph parameterization, x, y, and this time it's going to be 3. Your rx cross ry will equal to 0, 0, 1 again, and this time it is in fact going in the correct direction that we want for your outer, it's oriented going outward. By the way, this ORP is should be our orientation should be going negative, and so I forgot to throw in the negative sign because this ended up being 0. But if we were to do the negative sign, we would probably drop it in right here when we did the dot product. So that would be negative, negative, and this whole thing would be negative. But since it came up to be 0, that negative sign doesn't matter. For this one, we don't need to worry because this is preserving the orientation preserving parameterization. So we can keep this positive, not to worry about that. And when we do this setup of f of r of xy, it's going to be almost the same, x plus y plus z, which is this time is 3 instead of 0 from before. Y is y, and 2x minus y will remain the same. And when we do the dot product, you'll see, I'm going to put n here instead of saying rx cross ry. We get 0 again, and 0, and then you get 2x minus y. So that's going to give us the same thing. So our third surface flux integral is going to be the same as our second surface flux integral, which is equal to 0. So both of them ended up being 0. Yeah, you can catch it from here and here. Our domain, by the way, is the same thing also. I didn't mention that, but our domain is going to be the same. Okay. All right. So the total just ends up being 6 pi. So let's make a note of that. This is equal to 6 pi. Okay. Now let's do the right-hand side. So look at all the work that we did here to get the answer that we got, right? Now let's do the right-hand side. And just to exaggerate how easy this is going to be, I will do it in this little space over here. I guess I have to write kind of small. All right, first let us take the div of f, and that is equal to the derivative of the first component with respect to x, that's just 1. The derivative of the second component with respect to y, that's just 1. The derivative of the third component with respect to z, that's just 0. The div is actually a constant, which is great because if it's a constant, then we're putting a constant into a triple integral. So what do we have? The triple integral over E is this cylinder, of 2 dV. Well, remember what the triple integral of 1 dV over some object is. So that is simply the volume of E. And E is a solid cylinder. What is the volume of the cylinder? So volume is going to be equal to 2 pi RH. So this is going to be 2 times 2 pi. R is the radius, that's 1, and H is the height, that's 3. I'm sorry, it's not 2 pi RH. I was wondering because this is 6 pi. It's just pi RH. So let's try that again. The volume is pi r h, or pi r squared h. I think I found the surface area there. So the volume is pi r squared h of a cylinder. So there's a 2 here, and we have a pi, and then r is 1, and then the height is 3. So we get 6 pi. Almost fit. Let's move this just a tad bit over, and now you can see that it does fit. All right, so this is the area from the left hand side where we did 3 surface flux integrals, and this is a result from the right hand side where we use the divergence theorem, and we use the triple integral. So that's it. All right. This theorem is verified with this vector field and this surface. I hope that helps. Good luck.